When a pressure vessel ruptures in the vacuum of space, post-mortem analysis relies entirely on telemetry that made it back before the transmitter lost power. Historically, aerospace safety relied on these reactive investigations, studying wreckage to prevent the next failure. Today, the commercial human spaceflight sector is shifting toward a proactive, predictive model. The objective is to identify and mitigate anomalies long before they trigger a catastrophic event. Predictive safety requires an unyielding flow of high-fidelity telemetry. Without constant visibility into the health of a spacecraft's subsystems, a proactive safety framework lacks the necessary inputs to function. This diagram outlines the core components of an effective safety management system. Notice the critical weight placed on the data collection and analytics blocks. To accurately forecast failures, operators must continuously feed quantifiable data into their hazard models before human lives are put at risk. Because of this telemetry requirement, structural integrity alone no longer defines a vehicle's fitness for flight. In modern architectures, spaceworthiness is defined by continuous, unbroken data visibility. Maintaining this data flow in low Earth orbit is relatively straightforward. Applying it to the Artemis program, which operates in deep cislunar space, introduces severe physical and geometric hurdles. The primary data node for this deep space network is the Lunar Gateway's co-manifested vehicle, specifically its power and propulsion element. This schematic details the required data pipelines. The Gateway must maintain immense, high-rate communication links bridging Earth ground stations, the Gateway itself, and various assets deployed on the lunar surface. Guaranteeing this safety data pipeline means engineers have to overcome overlapping orbital, geometric, and spectral constraints. We are going to deconstruct the Gateway's RF architecture to see exactly how they are bypassed. The power and propulsion element handles both station keeping and orbit raising, while serving as the mission-critical safety relay for the entire Artemis architecture. Before addressing hardware, the first step to guaranteeing a data pipeline is solving the constraints of celestial mechanics. This simulation tracks the specific path selected for the Gateway, a mere rectilinear halo orbit. As the blue elliptical path shows, the orientation of this orbit prevents the Gateway from ever passing behind the Moon. It secures a direct, permanent line of sight back to Earth. The shape of the orbit dictates that the Gateway reaches Apollon, its furthest point from the lunar surface, at a distance of 70,000 kilometers directly over the lunar South Pole. Because orbital velocity decreases as altitude increases, the Gateway moves slowly through this high Apollon. This maximizes the line-of-sight dwell time, providing near-continuous coverage for astronauts and rovers operating in the South Polar region. By selecting this specific path, engineers remove planetary occlusion from the equation. The geometry of the orbit establishes the physical foundation required for a constant flow of telemetry. With the Moon no longer blocking the signal, the engineering constraint shifts to a more localized problem. The spacecraft blocks its own transmissions. The Gateway relies on massive, 65-kilowatt solar arrays to generate power. Along with docked visiting vehicles like the Orion capsule, these structures create severe physical obstacles for any radio frequency transmission. This plot models the line-of-sight blind spots for the starboard antenna over a single month. The cluster of red tiles indicates moments where the spacecraft's own geometry physically obstructs the signal path to Earth. Expanding that projection to a full operational year reveals the severity of the problem. The sprawling wave of red obstruction zones indicates that a single antenna yields an unacceptable level of signal dropout. Moving to the opposing port-side antenna produces a different but equally problematic map. The blind spots simply shift to a new location, leaving significant gaps in Earth visibility. To clear the signal path, the Gateway utilizes a dual-boom, steerable high-gain antenna configuration. The green and pink structures represent the extended booms that physically push the antennas past the obstructing solar arrays.
The operational protocol relies on active mechanical tracking. As the spacecraft rotates and an array begins to eclipse the signal, the system hands off the K-band and X-band links between the port and starboard antennas. This final graph displays the outcome of that active tracking. The clean blue wave contains 0 red blockage tiles, proving 100% spherical availability for the Earthlink. This level of availability is required because the Gateway must simultaneously maintain visibility with Earth while tracking assets on the lunar surface, as shown by these solid tracking lines. By combining precise structural geometry with active mechanical handoffs, the system engineers away self-occlusion. Securing the external signal path only matters if the internal hardware successfully processes the incoming data. Inside the gateway bus, telemetry and ranging signals are managed by software-defined modems, or SDMs. They are responsible for modulating and encoding the constant stream of safety data. Standard spacecraft typically rely on dual redundant systems. The gateway utilizes a resilient ring topology of 6 interconnected SDMs. This configuration provides extreme operational flexibility. If a single SDM fails, any of the remaining units can dynamically take over its specific data link without interrupting the broader network. This level of internal redundancy ensures that even during a hardware failure, the critical processing of safety telemetry continues. The final bottleneck in the data pipeline is an invisible regulatory one: international radio frequency spectrum rules governing the X-band direct-to-Earth link. The X-band must execute 2 conflicting tasks at once. It has to transmit low-rate safety telemetry while simultaneously turning around a high-rate signal used to calculate the spacecraft's exact range. This baseband spectrograph reveals the conflict. Combining standard biphase L telemetry with high-rate ranging creates the broad, unfiltered emission wave in the center. The purple line represents the strict spectral mask enforced by regulators. The gateway's combined signal bleeds past this legal boundary. This modulator schematic isolates the origin of that spectral bleeding. The biphase L converter and the turnaround ranging signal feed directly into a shared phase modulator. Engineers face a filtering catch-22. If they apply a filter after the phase modulator, they successfully narrow the spectrum, but doing so compromises the high-rate ranging data. The inverse approach is equally difficult. Attempting to filter the telemetry signal before it reaches the phase modulator is mathematically unpredictable, because phase modulation is a highly nonlinear operation. This baseband conflict forces a direct trade-off between international spectral compliance and the high-precision ranging data needed for safe navigation. When you step back from the micro-level mathematics of baseband filtering, the macroscopic scale of the Artemis cislunar relay comes into focus. The result is an unyielding flow of data, bypassing physical blockages and spectral constraints to bridge the void between the Earth and the Moon. This dense layer of RF engineering directly enables the safety policies that govern commercial spaceflight. High-level administrative demands dictate that telemetry must be continuous. The hardware realities of deep space dictate exactly how difficult that is to achieve. The advanced communication architecture inside the gateway is the physical manifestation of that rigorous safety culture. The system requires 3 distinct vectors of problem solving: the celestial geometry of the near-rectilinear halo orbit, the internal redundancy of the SDM ring, and the precise filtering of the baseband spectrum. These solutions work in concert to achieve the commercial spaceflight sector's goal, a complete transition to fully predictive hazard analysis. Deep space spaceworthiness is a composite of structural integrity and constant, high-fidelity data connectivity. A modern spaceworthy architecture ensures that predictive safety data is never blind, is never blocked, and never offline. In the harsh environment of cislunar space, true safety is an unbroken signal